Welcome to massive open online course on basic principles and calculations in chemical engineering. Here we are actually discussing about case study for a process, and in the previous lecture we have described the material balance of a chemical engineering process like cumene production from benzene and propylene, and there we have described the material balance, how and what amount of different raw materials are required for individual equipments and for the whole process that we have described. Still go through again that process for describing the energy balance equation here in this lecture. So basically that cumene is produced from the benzene and propylene at a certain temperature and pressure in a particular reactor, and then the product is being separated by different separator units like flash drum, distillation column. And before going to process those benzene and propylene for a reaction, that benzene and propylene feed to be heated up to a certain temperature for its reaction. So here in the slides, that description of the process with the layout is shown. Even we have described it in previous lecture also. Now in this case basically this benzene and propylene, those raw materials are coming from the storage tank, and this benzene and propylene after heating up by a vaporizer, those are mixed and then it is again heated up in a furnace to raise its temperature around 350 degrees Celsius for its reaction in the tubular reactor. And in the tubular reactor, generally the catalyst are being used as phosphoric acid that we have considered, and then the output of that reactor is actually sent to the separator through some vaporizer, where this outlet streams of reactor is utilized to heat up that benzene and propylene before entering to this reactor, and then outlet of those reactor and the furnace, whatever it is there. So after that it will be sent to separator, so that in the separator the reactor products will be separated, and that separation will be for just separating the unreacted materials, that is taking parts in the reactions. Now unreacted materials are here propane and propylene, also some amount of benzene will be there. So from the reactor, these unreacted propane, propylene, propane and benzenes, along with that products like cumene and a small amount of by products, that is DIPV, those will be separated in a separator, and there will not be only a single separator because in a particular separator you cannot separate all the products at a time. So for that, to separate the propane and propylene, one flash drum is used as a separator, where this propane and propylene will be separated, and it will be utilized for heating purpose in the furnace, and remaining that benzene, DIPB, and that is main product cumene will be preheated, and then it will be sent to one distillation column. It is called benzene distillation column, where benzene streams will be separated from the mixture of that benzene, cumene and PB, and in this benzene distillation column, from the distillate, that benzene along with small amount of cumene will be separated as a distillate product, and those benzenes will be recycled to that feed vessel of that fresh feed of benzene, and then it will be sent to again to the reactor after vaporizing. Now from that benzene distillation column, that cumene and byproduct DIPB, again it will be sent to another distillation column, which will be called as cumene distillation column. Now in that distillation column, you will see that cumene and DIPB will be separated from its distillate and bottom parts. So as a distillate, that cumene as a liquid, it will be coming after condensing, and it will be around 99.9% as per that requirement of production of this purity of this cumene. And from the bottom part of this cumene distillation column, that 100% of DIPB will be taken out, and it will be used for preheating of that mixture of benzene, DIPB and cumene, which is coming out from the separator of flash drum, and then DIPB used for other purposes. So in this way, whole process is actually going on for the production of cumene. Now in the previous lecture, we have described that what is the background of that reaction. Main reaction is basically propylene benzene, and which will give you cumene, and byproduct with that propylene and cumene will give you that diisopropyl benzene. And different sections are here: storage section, preheating section, vaporization section, pumping section, and also reactor section there. And in the reactor section, the pressure up to 25 atmospheric pressure will be considered, and the reaction will be done at 350 degree Celsius. And from that, after purification, we are getting that 99.9% of cumene. Now separation and purification section, that involves that flash drum, benzene distillation column and cumene distillation column, and we have described that process here, and then the details of that process description we have given in the previous lecture. Even also here we have mentioned in the slides there, and in this case you will see that the overall material balance, whatever we have done based on that mass conservation equation that is described in our earlier lecture, what is the principles of material balance and what is the governing material balance equations that we have described. As per those principles of that material balance, we have done the overall material balance, and this overall material balance can be done for whole processes if you are considering one single unit and what is the other unit separately there. So for those cases you have to do the material balance. You can do overall material balance, and also you can do the material balance for single unit or individual unit separately. Now in this case data assumptions are given. Here target is 500 tons per day of cumene production, where conversion of propylene is 99%, product molar selectivity is 31:1, and propylene whatever it is being used, that is 95% purity, remaining is along with that propylene is propane, and molar feed ratio of benzene to propylene to be maintained at 2:1, and top product of cumene separation will be 99.9 mole percent cumene, and remaining 0.1% will be byproduct. So in this case based on these data assumptions, we have done that material balance by considering that reaction stoichiometry, and also the selectivity of that reactions based on which we have calculated the what will be the amount of byproduct will be produced, that is given here. It is around 5.59 kilomole per hour as per assumed data for production of cumene. Now if we consider that individual unit for this whole processes here, and if we do the material balance, we can get different composition of that inlet and outlet streams. Now if we consider that feed vessel where that benzene, fresh benzene and recycled benzene from the benzene distillation column is mixed here, and then as an outlet it will be coming to the that mixture where propylene will be mixed to this mixed of this benzene from this feed vessel. So, according to that, what are the different components? First of all, we have to know that there may be fresh benzene, recycled benzene, that propylene, propane, cumene, para diisopropyl benzene, and what is the pressure and temperature. Now, all those components to be considered for all the equipments individually. So, in that case, if we consider feed vessel, what are the fresh benzene is coming, that is 178.75, whereas recycled benzene, that is coming from distillation column, it is 189.92 as per balance equation. The details of that balance equation and the calculation is given in our previous lecture. So, we are not actually considering that details here again. So, we are just summarizing for this here feed vessel inlet and outlet, what will be the composition of different compounds there. So, it is given. Similarly, for benzene vaporizer, propylene vaporizer, what are the different inlet and outlet compositions are given. So, according to that calculation, you will see that the same has already been discussed in details of that calculation given in the previous lecture. So, here just summarized of that calculation. These are the things for mixer and furnace also it is given. Similarly, for reactor, what are the fresh benzene is coming, what would the amount of recycled benzene is coming, and also propylene, what would be the requirement for that, propane, along with that propylene, what amount of that propane is coming. Cumene, also a small amount it will come, because the recycled benzene will contains that small amount of cumene after separation in the benzene distillation column. And then byproduct, of course, will not be there in the reactor, because 100% byproduct will be separating out from the benzene distillation column, and it is used for some other purposes. So, it is not being recycled there. And in the reactor, the pressure will be 25 atmosphere, and temperature will be 350 degrees Celsius. Whereas from the outlet of this reactor, the fresh benzene will not be there, because this benzene will be reacting and it will be consumed. And you will see that as per that reaction stoichiometry and the conversion, you can say that the unreacted benzene will be there, that is will be coming out from the reactor, that will be 189.92 moles, this is kilomoles, and propylene also, that will be unreacted, that will be 1.86, and propane, this is 9.80, which is coming along with that propylene, and cumene after production, this is the measure amount here, this is 180.52 kilomoles, and a small amount of byproducts which will be coming out from the reactor at that pressure and temperature of 305 degree Celsius. And then it will be going to the separator, from where you can say that top product of that separator will be coming. So, that propylene and propane will be separated, whereas in the bottom product, that recycled benzene and cumene and also byproducts will be coming out. And this bottom product of this separator will go to the feed preheater, the same amount, and it will be coming out also the same amount, but from the top you can say that PIDP will be coming out, because this PDIP will be used for heating purpose of this outlet of that separator. And then same amount of inlet of that feed preheater from the separator will be coming out from that feed preheater after preheating it, and then it will be going to that benzene distillation column, where you will see that only recycled benzene and cumene and a small amount of PDI PB will be separated, whereas in the top product of this benzene distillation column, it will be only recycled benzene and small amount of cumene, and the bottom product, the main product, that is cumene, will be coming out along with that byproduct there. And then this bottom product of this benzene distillation column again to be separated in a cumene distillation column, where input of that cumene distillation column will be the same, that is cumene and byproduct, and it is being separated and as a distillate only that cumene product will be coming, and at the bottom on that only DIPP will be coming. So, at this final cumene distillation column we are getting separation of this cumene and byproduct. So, we are getting here that desired purity of that cumene, and here that byproduct will be separated at the bottom product, which will be used for preheating purpose. So, in this way total procedure and the material balance and what will be the inlet and outlet proportions of that compositions are given here. Now, in this lecture main objective was to discuss that energy balance also. In that case, if we do the energy balance equipment wise for this process, we can say that for benzene feed vaporizer, if we consider first that because benzene will be sent to the reactor after mixing with propylene, and before that those propylene and benzene will be vaporized to a certain temperature. Now, this to be vaporized to at 40 degrees Celsius. Now, the stream of mixed feed of benzene and cumene is fed to the vaporizer with 40 degrees Celsius at 25 atmospheric pressure. So, there if we do the material balance there, we are having this benzene is 368.67 kilomole, cumene is 3.68 kilomole, total this amount, whereas mole fraction of those components will be here 0.99, 0.01 and 1 as a total, and similarly what would the mass fractions. Now, based on this you have to calculate in this vaporizer what would be the partial vapor pressure of those components in this feed vessel of benzene. Now, the bubble point and dew point of the mixture are found by using Antony's equation, that means how to get that bubble point from that Antony's equation. From those you have to first calculate what will the that vapor pressure, and from those vapor pressure what the respective temperature, that by that calculation you can easily get what should be the bubble point and dew point of that mixture by that Antony equation. And that Antony equation how to calculate already we have described in our earlier lecture. And then the vapor pressure is calculated at various temperatures to find the saturated temperature there, and in that case the vapor pressure for the benzene for this mole fractions it is coming 2587.64, and then cumene is 660.50 as per data here, and then what will be the that partial pressure of that benzene here that can be calculated based on this here, and what will be the total pressure for that, and what will be the mole fraction of that benzene accordingly, that is that can be calculated, and partial pressure will be for benzene is 2560.6007, and partial pressure of cumene will be 6.52. And here we can say that this P is basically a total pressure here, this total pressure in this feed vessel, and PV it is vapor pressure at 243 degree Celsius. So, at 243 degrees Celsius or 516 Kelvin the mixed feed will be vaporized there. So, it is called bubble point of this feed mixer. Now, heat required for vaporize this basically one should be that due to the rise in temperature, and also due to the phase change of that feed mixer. Now, for that for phase change of course you have to consider that latent heat, and for temperature difference that heat to be calculated based on that sensible heat like this is Cp into dT. So, heat required for the vaporize that it will be summation of that sensible heat and latent heat. Latent heat of benzene is here it is given that 23,773.63 kilojoule per kilomole, and latent heat of cumene it is given here 30919.2, kilojoule by kilomole, and average heat capacity of the benzene is given here 161.46 kilojoule per kilomole K. K is the Kelvin here, that is here Kelvin, and average heat capacity of cumene is given to 46.92 kilojoule per kilomole K. Now, what should be the then enthalpy, that means heat required for the vaporization of the benzene? It will be simply sensible heat with latent heat, that will be summation. So, it will be coming as here sensible heat will be simply Cp is 161.46, it is given to you, into temperature difference is what is that, earlier temperature is 40 degrees Celsius and bubble temperature is 43 degrees Celsius. So, you have to subtract this, and before that you have to convert it to Kelvin. So, it will be 243 plus 273 minus here 40 plus 273 plus latent heat, it is given here 23,773.63 kilojoule per kilomole. So, finally, the total amount is coming 56,550.01 kilojoule. Similarly, enthalpy of cumene can be calculated based on that summation of sensible heat and latent heat. As per this, that sensible heat is like this and latent heat is this. So, total amount of enthalpy per kilomole of that cumene is 81,043.96 kilojoule per kilomole. Now, heat required for the mixed feed, then it will be that what will be the fraction of those mixture of benzene and cumene. Accordingly, that heat required for the mixed feed will be here, this is the percentage of that benzene into its enthalpy of benzene, it is given, it is calculated as per this equation, and also remaining is basically cumene. So, as per that we can get that total amount of heat required for the mixed feed is like this 238,63498.19 kilojoule. For propylene feed vaporizer, similarly you can calculate what should be the heat required for those. Now, in this case propylene and propane fed from the tank is at 25 degrees Celsius at 25 atmospheric pressure. The stream is vaporized and heat to the temperature and mixed with benzene feed is at 243 degrees Celsius. Now, bubbling point and dew point of the mixture is about 62.5 degrees Celsius. Now, latent heat of propylene is given here 17,229.4 kilojoule per hour, and latent heat of propane is given here 17,611.41 kilojoule per hour, and then average heat capacity of the liquid propylene is given is 123.51. Average heat capacity of liquid propane is 125.48. The average heat capacity of gaseous propylene it is 82.86. The average heat capacity of gaseous propane is 97.48. And for liquid state, the Cp value for propylene is given 123.51, whereas it is for propane is 125.48. So, delta T is basically that bubble point temperature and tank temperature of this propylene propane mixture, and it is basically 62.5 minus 25, then it is coming 37.5, and then what will be the heat required for that liquid state to raise this temperature from 25 degrees Celsius to bubble point temperature of 62.5 degrees Celsius. So, finally, for propylene it is coming 463.625 kilojoule, and that for propane it is coming 4705.5 kilojoule. And for gaseous state for that propylene and propane, after heating it you will see that it will be converting to gaseous state. Since it is mixed to that 243 degrees Celsius. Of course, it is more than that bubble point temperature of that outlet stream of that benzene. So, there if it is mixed, of course, immediately that propylene and propane will be converted into gaseous state. So, for that what will be the heat there to converting this liquid state to gaseous state of that propylene and propane. So, for that at that gaseous state, that specific heat capacity of the propylene is 82.86, whereas it is for propane is 97.483, and their temperature difference of course will be from that bubble point to that benzene feed temperature of 243 degrees Celsius. Accordingly, it will be coming as 180.5 degrees Celsius. So, heat required for that it will be respectively for propylene and propane are 14956.23 and 17595.681. This is kilojoule per hour. Now, specific heat required for component of that propylene, propane, then we can say that heat required for the propylene, how to calculate that total amount of heat. One is for when it will be temperature change from certain degree to certain degree Celsius at its liquid state, and then converting that liquid state to the gaseous phase. So, their transition, that at that transition point of that liquid gas, what will be the heat required, that is latent heat, and again at that gaseous stage what will be the enthalpy change for that temperature change of that gaseous stage. So, for that heat required for the propylene, then finally we can say that after summing up all those whatever calculated here, based on which we can say that it will be total amount of 21861.08 kilojoule per kilomole per hour. Similarly, heat required for propane, similarly summation of that liquid state, sensible heat, latent heat, and then gaseous state, sensible heat, and summation of all those components, it will be coming out as final amount as 39912.5 kilojoule per hour. And also heat required for the feed, then accordingly what would be the total amount of moles for that propylene and propane. Accordingly, you can calculate here what will be the total amount of heat required for the feed. Then it will be coming as like here 4461676.28 kilojoule. So, in this way we can calculate that what should be the heat required for individual components for vaporizing it from a certain temperature to a certain temperature from liquid state to the gaseous state. Similarly, you have to do the energy balance for the fired heater also, where this feed mixture of propylene and benzene to be heated up to a temperature of 350 degrees Celsius. So, for that what will be the amount of heat required for raising this temperature of this reactant mixture of propylene and benzene to 350 degree Celsius. Now, for that we have to calculate what should be the enthalpy for that individual components of that mixture. So, compound basically before going to that fire heater is that propylene, propane, benzene, cumene, all those things, and their respective flow rate. That fire heater is already calculated based on that material balance. So, those amount are like this 186.20, 9.80, 368.67 and 3.68 respectively for propylene, propane, benzene and cumene. And then you have to calculate what should be a specific heat capacity for individual components when that temperature will be changing from 243 degrees Celsius to 350 degrees Celsius. Here it is very interesting that this specific heat capacity will be a function of this temperature. Now, how it will be related? This is basically related by this equation here given, that Cp will be equal to A plus Bt plus Ct square plus dt cube plus Et to the power 4. So, this is your specific heat capacity equation as a function of temperature. Now, based on this function, you have to calculate what should be the specific heat capacity within a range of this temperature difference of 243 to 350 degrees Celsius. Now, for that what you have to do, you have to calculate in this way that a specific heat for this benzene, it will be equal to integration of this limit of this 243 to 350 degrees Celsius of this for this here Cp dt, Cp in dt. Now, this will be coming as 243 to 350 Cp here dt, it will be simply that Cp is equal to A plus here Bt plus Ct square plus dt cube plus E t to the power 4 into dt, and then you have to that integrate it within this limit of this integration, and then you can get what will be the specific heat capacity. And for this A, B, C, D, E, all those are actually coefficients, and these coefficients are varying according to the compound or nature of the compound. Now, for the propylene that coefficients are given here A, B, C, D, E respectively in this column here, and similarly for propane these constants are given, for benzene also those constants are given, for cumene also those constants are given. So, once you know this or substitute this these constants here in this integrand and then do the integration, you will see that after integration you will it will be coming as A t plus B t square by 2 plus C t cube by 3 plus D t to the power 4 by 4 plus E t to the power 5 by 5, and then you have to calculate the limit of this integrand. Within this limit what will be the amount there. So, according to that for propylene it is coming that here 1.04 into 10 to the power 6 this amount of specific heat capacity for propylene. Similarly, for propane after integration it is coming 1.66 into 10 to the power 6 that means for propane. Similarly, for benzene it is coming 6.77 into 10 to the power 6, for cumene it is coming 7.29 into 10 to the power 6. So, once you know this specific heat capacity within this range of temperature, then based on this temperature difference of this 243 and 350 degrees Celsius, what should be the enthalpy? This enthalpy is basically what is that for the gaseous mixture. So, it is within that range of temperature change. So, accordingly that enthalpy can be calculated simply. What is that M that means here H will be or delta H to be calculated N into that Cp here into delta T. So, in this way you have to calculate. So, accordingly this amount respectively for propylene, propane, benzene and cumene can be obtained, and then total enthalpy after summation you can get it 2.73 into 10 to the power 9. Okay. So, in this way you can calculate what should be the heat required for that particular unit to raise the feed mixture to its certain temperature for further processing. So, we have described the material balance and energy balance for the production of cumene from the benzene and propylene based on their reactions, and also we have obtained the different input and output streams compositions based on that, and also what should be the enthalpy change for that different components in the particular units that we can calculate, and also we have given some calculations here. So, you can do the same way for other chemical processes for production of other compound there in a particular industrial scale operation. Let us do another case study here, like production of phenol by sulfonation of benzene and subsequent fusion with caustic soda. So, you can produce that phenol from the benzene by sulfonation process and also subsequent fusion with the caustic soda. This process is basically large scale batch cycle operation due to slow reaction step or fusionation of this benzene sulfonic acid with caustic soda. So, based on this principle, we can have this process layout for this production of phenol. Now, let us discuss this process flow chart for this production of phenol from this. Like in this case, you will see that benzene sulfonic acid is the first method to prepared by passing a vapor of benzene into concentrated sulfuric acid. In that case, the water formed during the sulfonation process is actually distilled out because sulfonic acid gets diluted and conditions accelerate backward reactions to the process. So, mainly here benzene is reacting with the sulfuric acid and giving your benzene sulfonic acid, and after that it will be neutralized, and then you will see that it will be fusioned at a fusionator with the that is caustic soda, and after that you will see that some oily layer of crude phenol will be produced, and then that oily crude phenol will be distilled under vacuum to get pure phenol, and in this case the yield is about 80 to 90% of the benzene. So, what are the equipments are being used here for this process? One is melter, and one is dissolver, and then evaporator, sulfonator, neutralizer, fusion pots, or you can say that fusionator, settler, and what is that you can say filter, acidifier, and then that vacuum still for distillation process. So, in this case first of all you will see that some sodium oxide will be melted from its solid to send to that fusion pots for the reaction with that benzene sulfonic acid, and before doing or sending this sodium oxide there, sodium salt there, what you have to do, you have to mix some sodium carbonate with water to make a solution, and that solution to be sent to the neutralizer for its neutralization, and in that neutralizer you have to send that sodium carbonate and sodium carbonate solution along with that benzene, and you can say that that sulfuric acid there, and after neutralization you will see that those mixture will be sent to that fusion pots, and where that sodium oxide will be reacted, and then you will see that unreacted benzene and that sodium sulphate that will be formed during that fusion reaction, and also you will see that some water will be there, extra water to be there, and to get that particular concentrated solution, that water to be vaporized or distilled there, and also there is settler where that sodium salt will be that settle down, and where that benzene will be again recycled to its fresh benzene feed, and from that settler after getting that mixture of oily phenol, crude phenol along with that sodium sulphate salt, it will be filtered out to separate that salt, and then remaining portion of crude phenol, it will be sent to vacuum distillation column, and there it will be that distilled to get that some percentage of or purified you can say that phenol there. So, this is the whole process here. So, for this process also you have to do the material balance and also energy balance, and what should be the respective temperature of different units, what will be the different pressure at different units, and also what will be the inlet and outlet streams and what will be their composition and amount, that you have to find out by this material balance and energy balance equation. Now, process description that we have already described, that this is a large scale batch cycle operation due to slow reaction step at fusionator. Sodium benzene sulfonate is fed to cast iron make fusion pots which already contains molten caustic soda there. Due to slow reaction with take about that 5 to 6 hours of resistance time, the pot is fed at regular intervals where continuous loading and unloading of the pot occurs for continuation of the process. The sodium phenoxide fraction which is obtained is fed to acidifier to produce crude phenol by reacting with sulfuric acid and sulfur dioxide there. Vacuum distillation column is used to get phenol from crude phenol, and remain salts are stripped in a steam stripper to remove phenol from them and aqueous salts. Crystallizers are actually used to increase the purity of the sodium sulphite which is coming out from that filter, and these crystals are separated from mother slurry by a continuous centrifugal separator, you can say, which is recycled to neutralizer again. So, based on this process we are getting this phenol. Now, in this case the process involves 4 major chemical reactions which are sulfonation, where benzene is reacted with sulfuric acid to form benzene sulfonic acid; neutralization, where benzene sulfonic acid is reacted with sodium sulphite to form sodium benzene sulfonate; and in the fusion reaction, the sodium benzene sulfonate is fused with sodium hydroxide to form sodium phenoxide; and in the acidification reaction, sulfuric acid and sodium phenoxide are reacted to produce crude phenol and sodium sulphite, and there it is separated. The reaction step explains the requirement of the unit operation equipment in the process are here filtration, distillation and crystallization. And sulfonation of benzene basically is reacted based on this. This is a reversible reaction that produces benzene sulfonic acid by adding sulfur trioxide and fuming sulfuric acid. The reaction is reversed by adding hot aqueous acids to benzene sulfonic acid to produce benzene. Now, to produce benzene sulfonic acid from benzene, fuming sulfuric acid and sulfur trioxide are added. Fuming sulfuric acid is a concentrated solution of dissolved sulfur trioxide in sulfuric acid. The sulfur in sulfur trioxide is electrophilic because the oxygens pull electrons away from it, because oxygen is very electronegative. That is why it will be regarded as electrophilic reaction, and the benzene attacks the sulfur and subsequent photon transfers occur to produce that benzene sulfonic acid. So, this is the mechanism how the reaction is taking place. Now, sulfonation of benzene is a reversible reaction that we know, that sulfur trioxide readily reacts with water to produce sulfuric acid and heat. Therefore, by adding heat to benzene sulfonic acid in diluted aqueous sulfuric acid, the reaction will be reversed. So, this is your reversed reaction. Now, here in this slides whole material balance and energy balance is shown here. See, for equipment wise the material balance is being done. If we consider that melter here, the what will be the chemicals are actually coming into this melter. It is basically sodium oxide and its amount is 471.74, and as a outlet what will be the amount is coming into the fusion pots, where it is given the same amount it will be coming after melting. And then in this dissolver you will see that sodium carbonate, the amount is given in kg here, and then here that water will be coming as there in the dissolver, and then you will see that after coming out from the dissolver, that it will be going to that neutralizer. There also what will be the amount of chemicals will be coming in. Basically this amount is coming here, but before neutralizer there will be sulfonator. There also you have to do the material balance. Here sulfuric acid coming this amount, and benzene is coming here after evaporator. In this evaporator, this amount of benzene is like this kg, and then accordingly also other unit, like what will be the inlet there and what will be the outlet there, it is given there. So, in the left side and the right side it is given inlet and outlet amount there. So, we can say that at a different unit we can do that material balance, and accordingly what will be the inlet amount to be required for that particular basis of production of 1 ton of phenol there. So, here in this case fusion pots, what will be the inlet, what will be the outlet, it is given. In the settler also what will be the inlet, what will be the outlet, it is given. Even in filter what will be the inlet and what will be the outlet, it is given there. And acidifier also, as per material balance, what will be the sulfuric acid required also it is given, and what will be the outlet portion of that is given as per this from this acidifier. And also after that what will be the amount of inlet and outlet of this vacuum seal also it is given schematically. And you will see that we have done also that that energy balance, and accordingly what will be the heat required for that individual unit, it is given here as heat column. You will see that different amount for different compound, different even different per unit. And also outlet also, what will be the enthalpy that is at the outlet composition are also given, and also inlet temperature of that this component, what will be that, and also outlet temperature what will be that is given according to that calculation. And also what will be the outlet amount of individual compounds also given, which is coming out from that individual unit, all are calculated. And in this way also you can calculate for a specific chemical engineering process there, and identifying that different units and reactions. Based on that reaction stoichiometry, what will be the input, what will be the output, and also you have to calculate that enthalpy based on that temperature change, that is sensible heat, and also latent heat if is there any compound is changing from its liquid state to the gaseous state. So, please go through this slide here again for understanding that material balance and energy balance and respective amount of heat and amount of stream at the inlet and outlet condition and outlet streams there, you can get it. So, I think it will be very helpful for your further understanding of material balance for the particular process in industry. So, I would suggest you to read further this textbook for your better understanding of different chemical engineering processes and also their respective calculation based on material and energy balance. I would thank you for choosing this course, and also I wish you healthy and prosperous life ahead, and of course all the best. If is there any query, please contact in this address. Email is given to these slides. Also website you can follow there. Accordingly you can mail me for further queries and also understanding. So, I want to stop for the lecture here. I welcome you to learn this course, and also wish you healthy and prosperous life ahead, and all the best. Thank you.